There are 3 different types of cheer: sideline, school competitive, and all-star competitive. Each are very different in their own way, but all involve the 3 concepts of stunts, jumps, and tumbling. For my presentation, I'm going to focus on the physics involved with stunting. Stunting involves a flyer with a person or group of people underneath them. Stunts range from shoulder sits to one-legged stunts to basket tosses like the one shown in the picture on the right. The first concept related to stunting is center of gravity. Simply put, a person's center of gravity is the point where gravity is considered to act. When a person stands balanced, their center of gravity is around their core. When people shift so that their weight is unequal, their center of gravity moves away from their core. In cheer, the flyer stays in the air when their center of gravity is in line with the base's support. When the flyer's hips, legs, or torso move too far away from that imaginary line, the stunt falls. However, flyers can still hold positions in the air that are different from a normal standing position, like in the picture on the right, as long as the flyer's weight is balanced so that their center of gravity remains in line with the base's support. This is a video of my stunt group working on a stunt. The stunt came close to falling because I shifted my hips too far to one side, which moved my center of gravity along with it. However, I corrected it fast enough for my bases to adjust. One of the most important aspects of stunting is catching the flyer in a way that keeps both the flyer and the bases safe. This involves the concept of impulse, which is the change of momentum of an object due to an applied force over a period of time. When catching a flyer, the bases are applying an upward force that works against the momentum of the falling flyer until they come to a stop. The equation to calculate the impulse of a scenario is the magnitude of the applied force multiplied by the amount of time that the force is applied for. These 2 factors are inversely related, so as one increases, the other decreases. This gives the bases 2 options for catching the flyer. The first providing a large force against the momentum of the flyer for a short period of time, or the second is allowing more time for the flyer to be caught by anticipating and absorbing the catch, which requires a smaller applied force. With the first method, the bases would keep their legs straight and their arms in a position where their forearms would make a 90-degree angle with their body and keep them there until the flyer is caught. This is usually done by bases newer to stunting who expect their flyer to fall nicely into their arms and are not aware of how dangerous this technique can be. By not bending their legs and keeping their arms stationary, the bases provide only a few seconds to slow the flyer's momentum. In my 11 years of cheering as a flyer, I have seen way too many injuries as a result of catching like this: concussions, stitches, and even a few chipped teeth. Even if the injuries don't happen immediately, over time catching like this can lead to ankle, wrist, and especially back problems. The second option is a much safer method. By extending their arms like in the picture on the right, the bases are anticipating where the flyer will fall and are giving themselves more time to slow the flyer's momentum. This is a video of my friend's stunt group. I'll play it once now and then again after I explain how it relates to my concept.
5, 5, 7, 7, 1, 1, 3, 3, 5, 5, 7, 7, 1, 1, 3, 3, 5, 5, 7, 7, 1, 1, 3, 3, 5, 5, 7, 7, 1, 1, 3, hands, 5, 5, 7, 7, 1, 1, 3, 3, 5, 5, 7, 7, 1, 1, 3, 3, 5, 5, 7, 7, 1, 1, 3, 3, 5, 5.
While the entire stunt was cool, I'm going to focus on the section on the flyer's twists and how they relate to the physics of rotational inertia. Rotational inertia is similar to inertia with linear motion in that it is dependent on mass, but rotational inertia also depends on the distance of the object from the axis that it spins on. In this scenario, we can assume that the flyer's axis is an imaginary line that connects her head, center of gravity, and her feet. With her arms and leg extended away from her imaginary axis, as she has just before the throw, her rotational inertia is high. Larger rotational inertias indicate that an object will rotate around an axis with more difficulty, thus more slowly than it would with a lower rotational inertia. When the flyer brings her legs together and tucks her arms in closer to her chest, she is lowering her rotational inertia. This increases her rotational speed, which allows her to complete 2 spins before being caught by her bases. This also applies to the 1.5 spin that the group does towards the beginning of the clip. The flyer keeps her arms and non-supporting leg close to her body during the spin until she finishes to the front in a heel stretch. Raising her arms and pulling her leg up into a heel stretch slows her rotational speed. If the flyer did not wait until she reached the top to do this, she might not have had enough time to finish the spin and the stunt could have fallen. Rotational motion plays a large role in stunting. I'll play the video one more time so you can see what I'm talking about if you didn't catch it the first time.
5, 7, 7, 1, 1, 3, 3, 5, 7, 7, 1, 1, 3, 3, 5, 7, 7, 1, 1, 3, 3, 5, 7, 7, 1, 1, 3. Hands, 5, 7, 7, 1, 1, 3, 3, 5, 7, 7, 1, 1, 3, 3, 5, 7, 7, 1, 1, 3, 3, 5.
In the time since it was created over a century ago, cheerleading has evolved from a simple yelling to impressive tricks and flips that are almost as interesting as the physics behind them.